So our current working theory of the universe is called the Big Bang Theory. The basic idea is we know now that the universe is expanding, and if we could watch the reverse of that, we would have a universe that's contracting. If you go back in time, there must have been a time when all the galaxies were all mushed together in one big blob of matter, and the universe must have expanded or exploded from the initial high-density state. Now, in fact, many people think of this as a small chunk of energy expanding into a pre-existing emptiness, but that's misleading because, in fact, what happened to the entire universe. So, if you ask where did the Big Bang happen, well, it happened everywhere because it happened to the entire universe. A little difficult to comprehend, I understand. I don't truly comprehend it either, but just kind of accept it. Since expanding gases cool off, and we can think of the universe, especially in its early days, as kind of a blob of gas, the universe was much hotter when it was highly compressed, so its energy density was much higher. So what that means is if we look really, really far back in time, we should see a very, very hot universe. Okay? But before we get to that, let's talk about how old we think the universe is. How long would we have to run our imaginary movie back in time? How long would we have to rewind our movie of the expanding universe before we got to the beginning? Well, it's actually pretty easy to figure out. We know now that the velocity of galaxies away from each other is given by the Hubble law. The age of the universe we can estimate, or at least get an approximate age of the universe, if we divide by the distance between galaxies by the velocity that they're moving away from each other. Okay? But, okay, well, let's do that. So time is equal to distance divided by velocity. This is, when you say that you live 2 hours from a friend, basically what you're doing is you're dividing the distance to that friend divided by the velocity, the average velocity that you drive your car to go to visit them. So it's a very basic equation. Time is distance over velocity, and that's because velocity is distance divided by time. However, the Hubble law tells us that the velocities that galaxies are moving apart from each other is proportional to distance. So these two things are not independent of each other when we talk about the expansion of the universe. We can substitute velocity with the Hubble law because the velocity here is actually the Hubble constant times the distance. If you go back a few pages in your notes, you'll see that. So since velocity is h naught times d, is the Hubble constant times distance, we just take this and plug it in for v, and that gives us that the time that the universe has been around is the distance between galaxies divided by Hubble's constant times the distance between galaxies. The two d's cancel out. This d cancels out with this thing, and all you got is the inverse of the Hubble constant. The inverse of the Hubble constant, it turns out, gives you a time. Okay, Hubble constant is in kilometers per second per megaparsec. However, you can change megaparsecs into kilometers, and then the kilometers go away, and the Hubble constant actually has units of inverse time. So if you have 1 over the Hubble constant, you have units of time. It's amazing that I can say this right now, because for most of my career, this was unknown by a factor of 2. Scientists didn't know the age of the universe. They knew it was somewhere between 10 and 20 billion years old. But it has now been pinned down to a ridiculously good estimate. And that is, our universe is 13.7 plus or minus 0.1 billion years old. That was a long time in the making, but we're pretty darn confident that that's what it is right now. All right, now, we gave you 2 pieces of evidence that the universe started in a Big Bang and not a steady state. We said that the early universe had lots and lots of quasars, and also we see that the universe has chemically changed from stars that were entirely made of hydrogen and helium to stars that have at least a few percent of heavy elements today. We, in fact, and the Earth around us, are examples of how the universe has changed. You couldn't have made a rocky planet like the Earth in the early few billion years of the existence of the universe, because there just wasn't any silicates, no mineral materials to make a rocky planet out of. The real nail in the coffin to the steady state theory, however, came in the mid-1960s. With the discovery of what we call the 3-degree cosmic microwave background radiation, or just the cosmic microwave background radiation, or CMBR, as it is often abbreviated, because it's kind of a long title. In 1964, some astrophysicists at Princeton calculated that there should be radiation left over from the Big Bang, or at least a time shortly after the Big Bang, when the universe was very hot. The early universe was not only hot, it was opaque. In other words, it was like the interior of a star. It was like the interior of the sun. When you look at the sun through a properly filtered telescope, it looks like it has a surface. But in fact, it has a photosphere. And inside that photosphere, it's still a gas, but it's an ionized gas. It's a bright fog. It's kind of like a shimmering fluorescent light bulb, okay? The kind of energy-saving bulbs we have today, or those long tube lights that we've had for quite a long time. When it's shining, that's a hot gas in there, and that hot gas cannot be seen through. So what these scientists said was that the universe was several thousand degrees, and it was a hot, shimmering gas. So why, when we look far away in space, don't we see a wall of light, a hot, shimmering wall of light that has basically a blackbody spectrum, a thermal spectrum, with a temperature of several thousand degrees? Well, the reason is that when we look at great distances, those regions of space are redshifted away from us. So those photons, which would normally be in the visible part of the spectrum, like the photons you get from a fluorescent light tube, have been shifted all the way over into the microwave radio region of the spectrum. So this radiation should have a thermal spectrum, but should be highly redshifted, since it's coming distances of almost 14 billion years. Regions of the universe that, in fact, have been expanding away from us for 14 billion years. It should be most intense in the microwave portion of the radio spectrum. And in fact, shortly after its prediction, of scientists just a few miles away in Homedale, New Jersey, at Bell Labs, accidentally found the radiation. This is Arno Penzias and Robert Wilson. I can't remember which one is which. But these two fellows basically were using this old horn antenna, which was one of the first antennas to communicate with satellites back in the early 1960s. They were going to use it for some radio astronomy, and they found a uniform hiss of radio radiation coming from all areas in the sky. And they thought that this was a problem with the receiver at first, so they checked their electronics, but nothing seemed to work. They even looked inside the telescope and found that there were some pigeons roosting in there. So they cleaned out the pigeon droppings, which they thought might be making the noise. But the noise was far more important and far more persistent than the thermal radiation from pigeon droppings. It turns out to be what they eventually called the echo of creation. This was, in fact, the hot radiation from the early Big Bang of the universe, the early time when the universe was extremely hot. And this showed that truly the universe was very, very different in the distant past than it is today. So the steady state theory could not possibly explain that. Here, in fact, is the beautiful black-body curve. It's beautiful because it's just about perfect. This was taken by the Kobe satellite in the late 1990s, and it's just about perfect. It shows that the peak wavelength is around 2 millimeters. That when you get the exact peak wavelength, you find that it's the temperature of the universe is 2.725 plus or minus 0.001 degrees Kelvin. That is an incredibly accurate number, and that's the average temperature of the universe as it is now. And as the universe continues to expand, it will continue to get colder and colder. As I said, this was the final nail in the coffin for the steady state theory. shows that the universe was once a dense ionized gas with a temperature of thousands of degrees. Now, one problem I always had when I first learned of the microwave background is, why doesn't it run out? If this is the echo of the Big Bang, if this is the radiation from the Big Bang, why do we continue to see it tomorrow? Why don't we see it once and then it's gone? And the answer is, okay, because every day we see one light day farther into the universe. And since I can't really draw here, which is what I usually do, let me just show you a diagram. Here we are in the middle, exaggerated in size, and we can see out to 13.7 billion light years. So we can see in every direction 13.7 billion years into the past. So let's pretend that today is the 13.7 billionth birthday of the universe. Well, tomorrow we will be able to see one light day farther into the universe. And the day after we'll see one light day farther into the universe. And so on, and so on, and so on. So every day we're seeing a little bit more of the universe with our radio telescopes, and we see radiation coming from farther and farther parts of the universe. So there's plenty of universe out here that we just haven't had time to see. We call this distance the cosmic light horizon. The amount of time we've been around since the beginning of time, or at least from about a few 100,000 years after the Big Bang, is the farthest we can see. The Big Bang is probably somewhere around here. We can never really see there because this part is opaque to us. And so we can't see light coming from farther than this event horizon because of the opacity. If we could somehow use, say, neutrinos or something that go through the gas, then we'd be able to see back to the beginning of time. Okay, well, there's a complication. Conventional wisdom has always suggested that gravity would ultimately slow down and maybe even halt the expansion of the universe. So here's a graph of the Big Bang, the expansion of the universe, and then enough gravity to bring everything back together to a big crunch. Okay? That's what we would call a decelerating universe. Here you have kind of what's called a critical universe, where the expansion proceeds and then just very slowly proceeds forever, except it slows sort of asymptotically to zero. Here we have a universe that is just coasting. There's so little mass in it that it just keeps expanding and expanding forever without shrinking at all. And here we see something that no one thought was possible, an accelerating universe, where the expansion continues to get a little bit larger with time, and the universe keeps accelerating, and so the expansion will be greater in 1 billion years than it is now, and 2 billion years from now it will be even greater. This was first discovered to be true by using those type 1a supernovas we talked about in the last unit. What it showed, because we could see galaxies so far away, close to the beginning of time, is that the expansion of the universe is actually accelerating. And if this is true, there must be some repulsive force, some sort of kind of almost an anti-gravity pushing the universe apart faster and faster. Astronomers have a word for this, although they don't know what it is, and that word is dark energy. So in addition to dark matter, which we don't know what it is, we have dark energy, which is also something we don't know what it is. This mysterious force, they think, may come from the energy of virtual particles that pop in and out of existence in the vacuum of space. And for some reason, when more space is created by the expansion of the universe, it actually makes more of this energy, which pushes the universe apart faster and faster. This is sort of the frontier of current astrophysics. We don't know what this stuff is. It may be a long time before we do. But I think this is probably a decent place to end the course. So that is all. Hope you enjoyed it.